Okay, morning everyone. So what we're going to do today is we're going to talk about motion again, except I'm going to give you the graph. Okay, I'm going to give you guys the graph. So here is the example of motion with graphing. So I'm going to give you a graph that says this is my v of t, which is my velocity function. And I'm going to say this goes at, this is 3, go all the way 3 to, let's say this is 4 and 6. We're at 6, we go backwards to -2, we'll go all the way up to 10. Okay, so what was the distance traveled from 0 to 10? Oops. So let's talk about what happened here. Let's say I'm riding my bike, and we can call this miles per hour. Or maybe this is me running, right? It's always some type of movement, right? So I'm at a constant velocity from here to here till about t is equal to 4. At t is equal to 4, what happens to my velocity? Do I speed up or do I slow down? I start slowing down, right? I start getting tired. I start slowing down. Or maybe it's a stoplight. Maybe it's me going up a hill. Maybe it's something happened. But the idea is my velocity is slowing down. But I am still gaining distance. These are still positive velocities. But I'm just not going as fast. So I'm not gaining as much distance. At some point, looking at 6, I stopped. And then I turn around. And what happens when my velocity is negative? That means I turned around, stopped, turned around at t is equal to 6. So these are just some notions I'm catching here. After t6, I start picking up my speed, going backwards. But I'm not as fast as what I used to before because I only get up to 2. And then I go from this point, let's say this point here is, we'll call that 7, okay? From 7 to 10, so you guys can see that 7 to 10, we are going at a constant speed of -2. So if this was on a one-dimensional line, right, I went forward, hit a spot, and then I started coming backwards. I went forward. After a certain time period, I started coming backwards. Okay, and this is our S of t graph, I guess. S of t, because it's only, not even S of t, it's more like our S. All right, so the question is, what is the displacement? How far have I moved from my initial position? So if my initial position was 0, let's say t is equal to 0, S of 0 is 0, okay? How far have we moved? So what we do is just like what we did before. The rule is that to find displacement is integral from 0 to 10 here of v of t. Now v of t is given by the actual graph. And unless you want to multiply all the vt's by a little bit of dt, this would be a waste of our time. So what we mentioned before is an integral is another way of looking at area underneath a curve. And the curve for us is v of t. So let's go ahead and just find the area underneath this curve. Now careful, there are positive and negative areas. There's a couple ways of doing this. You can use rectangles and triangles. You can use trapezoids if you want. So there's a couple ways of breaking this up. So we can say it's 3 times 4 is, like a rectangle, right? That's a rectangle. And then we add a triangle to that. Half base times height. So it's 2 times 3. Half base times height, it's 3. On the bottom part here, I'm drawing the shapes, okay? I'm drawing out the shapes here, okay? That's 1 times -2. That's -1. And the last part here is 3 times -2 is -6. Would that have changed if,
If,
did I make a mistake? Hopefully not.
no, I was just asking Mr. Ko if we don't have the full equation, we just block it off and then find the area of each.
Right, so oftentimes when you're given a graph like this, there is no one polynomial or one equation that fits because we go from lines to like constants to lines to constants again. So this is actually a piecewise function. And I don't think we want to deal with a piecewise function that says, okay, between y is equal to 3, so v of t is equal to 3 between 0 and 4. And then it switches to a y equation between between 4 and 6. And then after 6, it becomes negative 2. After between 6 and, no, sorry, 7. That was a 7. Seven and 10. Like, this is what the equation would have actually looked like. It'd be a piecewise function of 3 different sets. And if they gave us this, that's fine. You would just find the integral of 1, 2, 3 parts separately, and then add them all together. That would have been totally fine. But it's easier because they give us a graph, and the graph is made up of nice lines. So if we add this up together, I want you guys to notice that in my positive velocity mode, we went a total of 15 units, whatever that is, forward. So we went up to 15 here. And then we started taking away some. We went back minus 7. So where are we at? We're at 8. So one of the skills that we want to be aware of is that if they give me the picture of velocity, the area underneath the velocity is the distance traveled. Perfect. And that's how easy some of these questions can be. But the problem is wrapping our head around it to figure out what was given and what can we use. Now, would this question have also worked if I just used 2 trapezoids? 2 trapezoids are half base times height. Half of base is 4 plus 6. And then the height was, let me throw a 3 there. I always forget to write the 3 first. 1/2, 3, right? That's my height. And this would be 10, oh, that's a 2. This is 10 times 3 is 30. Half of 30 is 15. Yeah, that's 15, right? That also worked. On the right side, if I want to say from 6 to 10, it's 1/2, 4 times negative, oh darn it, what am I doing? I picked the wrong number. The height here would have been like negative 2. And 4 plus 3. 4 plus 3 is 7. And this would be negative 7. Okay, just to show you, both of these techniques will work if you use trapezoids or rectangles and triangles. So whichever one you think is easier. Okay, why are these problems important? Because sometimes on a test they will give you these types of models. Let's go ahead and take a look at your homework today, and we'll see this model given. Okay, so on your homework, you guys have questions like this, where I actually just give you a picture of this. Some things you want to make sure when you're given this graph, you want to make sure is that this is velocity, right? That's velocity. Because when I find the area of velocity, that's our distance traveled. And then we see that this is time. And what's velocity times time? Velocity times time is distance. Okay, that's the big deal. That's our physics idea. Why does this work? Because velocity times time is distance. So the area of these are considered distance. If this is velocity, don't try multiplying by time, because that's going to give you something else. So the question is, a particle is moving along the x-axis. Okay, thank you. Let's move along, so it's in this one direction, right? Particle going back and forth, right? Its initial position at t is equal to 0 is 15. Okay, so wherever we're starting at 15. The figure shows a graph of the particle's velocity v. The numbers are the areas of the enclosed regions. Great, they did all the work for me. The first region is 12, the second region is 8, the third region is 14. What is the total distance traveled by the particle between 0 and c, wherever this ending value is? What is the total distance traveled? Now, in calculus, we had a specific way of talking about total distance. It was the integral of the absolute value of your velocity. Why? Because I don't care if you go backwards. I just care that I add up all the values. If you go forward, I add it. If you go backwards, I add it. It's not like when you turn around in your car, you don't get gas back, right? That'd be super cool. Imagine if the teacher said, hey, run a mile and then run backwards a mile, and then you didn't run at all today. Okay, that doesn't work that way. So the question is, first, what is the total distance traveled by the particle? Now, looking here, we traveled 12, and then we turned around and we traveled 8, and then we turned right back around and then we traveled 14. These look like, remember when you run suicides in PE? You run forward, then you run backwards, then you run forward again. Okay. So how much distance did you travel? You traveled 12 plus 8 plus 14. And that gives us 34. And they told us this is in centimeters. Okay, so make sure you do state the unit if they do give you the units. But why did they give us this initial term? In this case, it is not useful. If I ask you though, what is S of C? What is the position at C? C, remember, was our final value here? What is the position of the particle at C? Okay, now this changes it because this is a different question. Okay, we're looking at a different question now, right? Different question, but we're going to use all the same ideas here. What is the position of C? Sorry, of my particle. So that's our position S. Now, I'm going to draw this out a little differently. I'm going to draw this a little bigger, okay? We started off at 15. Is everyone okay? Sorry, they call it X here. X, let's use X then, fine. X of 0 is 15. What happens next? Well, we go to A. Don't we add 12 plus 12? Darn it, that looks ugly. Plus 12. We added 12. So now the particle went all the way up to 27. What happens after the particle goes up to 27? We're now here. It turns around and it goes back 8. So it goes back 8. So if you go back 8 from 27, we're at 19 now. We're at 19. So we minus 8. And then what? I turn around and then I go forward again. Then I go back forward. And we add 14 to that. So we add 14 to that. That's 20, 33. We're now at 33. So where's my position? We're at 33. If I ask you a different question, what is the displacement? Displacement takes what is your x of c minus your x of 0, right? What is your final position versus what is your initial position? So let's figure out how far we moved. And it's really this portion of the graph, but that's just start fresh. I'm starting off here. My first move is forward by 12. I add 12, right? After we move 12 here, right? We move 12 here. We go back 8. So we're now at 4. After 4, we add 14. So we're going back forward. So we add 14 to that. So we're over here at 18. So our displacement is 18 centimeters from the origin. Now here's something I want you guys to realize. How do we find this guy here? What it is, it's you take your displacement and we add it to your initial. So you take your displacement, so you say x of 0, your initial value plus displacement. You take your initial value and then you add displacement to it. So some problems, they're going to give you the velocity, and they're going to tell you you had a starting value which was not 0. So you take your displacement, how far we've moved, and we add it to our initial value. It's almost like the stock market. Okay, if I tell you I start off with $1,000, that's my initial value. And then I won and lost throughout the day. I made $100, I lost $20, but then I gained another $40. How much money do I have now? And that's always your change, your displacement, plus your initial that we started off in the day. And this is the idea of working backwards also. Okay, so we're working on a couple different questions here. But this one here was actually pretty easy. Actually, no, did they end up asking a couple of questions? Remember how these are multiple? Yeah, what's up?
Can you explain this again quickly? My volume wasn't working. And
just watch the video again later. Just watch the video.
All right.
And if you don't get the video, just email me, and then I can work with you there. Okay. All right. So we said our answer here was, what was the answer? I forgot.
34.
Oh, thank you. Let's see what happens when I write 34 here. Because remember how these are multiple steps? 34. 34? Is that right? Okay. Good job. Next question. Remember? Oh, that's it. That was only one part? What? I thought this was like multiple parts. Never mind.
So we can just add up the numbers in the graph?
Remember, it's always about depending what type of question they're asking. If they're asking displacement or total distance. So let's look at this question. It's very similar to that. Approximately where the... No. This is a different question. Okay. Let's go back to that last question, actually. So if the question is total distance, we said, if the question was total distance, our equation for total distance was the integral from A to B of absolute value of Vt, dt. Meaning all the negatives became positive. If the question is, sorry, darn it, I should write this better. Total distance. If the question asks you for displacement, then the equation was the integral from A to B of V of t dt. So we take the positives as positives and the negatives as negatives because we went backwards in those negative values. So I went forward, backwards, and then forward again. So this would have been 12 minus 8 plus 14. Over here on top, it'll be 12. The absolute value of negative 8 becomes positive 8. And then we add 14.
Mr. Cole, I got confused about the second value that we got, 33. What was that?
Oh, 33 was me talking about a different problem, about what position were we at. If we started at 15, and then we went forward by 12, back by 8, and then forward by 14, where would we have been?
Oh, okay.
Okay. And that was displacement of 18. We said in this problem the displacement was 18. And if you started your initial at 15, 15 plus 18, that tells us our total change, our final position of 33. And we did that a couple of different ways. Okay, let's look at that next problem. Now, this question is asking, a particle moves along the x-axis. Its initial position is 0, and and starting initial position is 15. The figure shows the graph of the particle's velocity. Great, thank you. The number of areas are enclosed by the region. Perfect. Approximate where the particle achieves its greatest positive acceleration on the interval between 0 and B. Okay, so positive acceleration. Now, what is acceleration in comparison to velocity? We said acceleration. Sorry. We said acceleration is equal to, so V of t, sorry, A of, oh my gosh. A of t is equal to the derivative of V of t. So what I want you guys to do is practice your graphing skills from before. And can you graph the acceleration graph based on this velocity graph. You guys remember how to do that? How do I graph how would I graph the derivative based on this previous graph? Here's the first hint if you forgot. Graph the derivatives at 0 first. Graph the derivatives at 0. At what point would we have a derivative of 0? 0, 0, 0. These are our first graphs. We have a 0 here, 0 here. Those are always the easiest parts to graph when the derivative is 0. Now between this point and this point, do we have a positive slope or negative slope? Positive. Good. Thank you. Thank you for mouthing like those words, folks. I can see that you guys are saying positive. Good. That's positive. From point here and here, see how this is negative, right? So we have a negative slope. So at what point do we have a positive acceleration? The maximum, they're asking for the greatest possible positive. It's going to be someplace around here, ish. Something around right here. That area-ish. And I'm guessing it looks like it's going to be point A now, right? Because they gave us a point A. Okay. But our estimate was pretty darn good, right? Our estimate was something in this area. Yeah, something in this area. That's my greatest positive acceleration. That's when my velocity is increasing the most. That's when I'm kicking on that gas pedal. Okay. Let's go ahead and I'm gonna save this PDF for now, and oh, good luck with
Wait,
that.
so how did you transfer it over?
Okay, darn luck that I saved it, right? Now the problem is I need to find out where I saved it at. Look at all these pictures of me. Went to my files, saved it as a, where'd it go? Here it is, first one.
Do you delete all those pictures at the end of the year?
Do you delete all the pictures on your phone at the end of the year? No. Do you know why?
I mean, of
Because you're
homework.
lazy.
I do.
Because you're lazy, just like me.
I got Google Photos. I just go and delete like whatever I don't want.
Oh yeah. Okay, so so this problem here is, first things first is we want to make sure we understand the fundamentals. The fundamentals is that they're asking me for acceleration, but they gave me freaking velocity. So the way we get from acceleration from velocity is we take the derivative. And we realize that I can graph derivative is really darn easy. Like, don't overthink it. But you have to know your fundamentals. And one of the fundamentals is that we always remember that we graph the derivatives at 0 first. Right? Are you okay? Those are tangent lines. Those are zeros. So I copied 0, 0, 0 down. What happens between my first 0 and my second 0? That's a positive change, isn't it? So we know the graph is going to go up and down. Now, why is it curved? Why isn't it like a robot? Why isn't it like a triangle? Why isn't it just a straight line? And the reason why is, look here. It's almost like a roller coaster, right? This curve here starts to get more and more and more and more curvy. Super curvy, and then slows down. It's almost like a roller coaster ride. Whenever you go over the crest of a roller coaster, right? It goes slow, fast, slow. And that's what actually is happening here. It's slow change, big change, slow change again. But they're all positive changes. I'm adding to it. I'm still adding positively to it. Once we hit the 0, I'm starting to subtract from it. So my acceleration starts to hit the brakes on me. So I'm hitting the brakes now. So my velocity is now dropping. You don't drop your velocity unless if you apply a negative acceleration, right? You don't slow down unless you hit the brakes. So this is where we're hitting the brakes, force in the opposite direction. So this is all dragging down my velocity. I am hitting the reverse. Now, how did I find what they asked for? They asked for what's the greatest positive acceleration. So I looked at my positive acceleration graph here. Oops, darn it. I looked at my positive graph, my acceleration graph. I said, well, hey, look, isn't it the most positive right here? And we can find that also by taking the derivative. You can go back to 0 if we really need to. And if I'm just walking it up to my previous graph, it's about this area here. But hopefully, you can also just see it. When is this acceleration positive looking at a velocity graph? We said that the acceleration is the change, right? That's just a change of velocity. And that's just another way of saying derivative. which is another way of saying slope. So when does it have the most positive slope? The most positive slope happens, actually, you know what? Yeah, the most positive slope happens. This is a little slope, this is a lot of slope, and this is a little slope again. This could have happened probably over here, but but this actually is continuing to get more positive. Okay, let's go back. Oh. And we said the point was A. Let's check our answer. Oh yeah, good job. Oh, that's it? There's only one? Oh, the next question changed, right? Now, if I want to look for a similar question, they change the question. And this question, without even doing the work, right? The question is still the same. What is the greatest positive acceleration for this graph between the choices of A, between A and C? Well, the greatest positive is going to be at B.
Wait, was that acceleration or velocity?
That was acceleration again. This is the same question. I was asking about acceleration. When's the greatest acceleration?
Wouldn't that be the first point though? Because
It was
that's when
negative.
the graph goes up.
It was going down. Oh, for that last point? Let's take a look. Let me take a look. Oh, they asked specifically between A and C. If you looked at the question, I'm sorry, they actually asked and said, hey, between A and C only.
Oh, so even if it's going down, it's still a big acceleration?
Yeah, that could be acceleration. But they asked you specifically for a positive acceleration. They asked specifically for a positive acceleration. These graphs it's giving me a new problem every single time I'm flipping this. So for this one here, the greatest positive would have been between A and C is going to be right here, going that way. For the problem that flipped it, let's see if it's going to flip it here. Okay, look at this one. This is a negative acceleration because the derivative of velocity is acceleration, so that's the tangent line. And this would be the greatest positive because we're increasing.
So we're going off which graph? The one that we drew or the one that's provided?
We could, the point is that we could go off the graph that we draw. Let's draw ours. 0, 0, 0, right? Negative, positive. The most positive will be like kind of right there, which is our B value. But I also want you guys to realize that you don't have to draw this. This is helpful to us to have like a fuller understanding. But we can also think of acceleration as just the slopes of velocity. So when do we have the most positive slope in this graph? Let's draw some slopes here, okay? The slopes are negative, super negative, lightly negative. I just call those our negative slopes. That's our acceleration. Stop, right? And then on the right side, we start increasing slowly, really fast, and then we slow down and we stop our acceleration. So which of these would be the most positive acceleration? At A is our negative acceleration, and B is our positive acceleration, our positive derivative. So we don't even have to draw the second graph. This graph is helpful to us, and in some problems, sure, we have to draw the second graph when we were trying to find that term. But this is more conceptual. It's kind of just getting us to that idea. Okay, Jacob?
Yeah, that makes sense. Thank you.
Perfect. He just says it makes sense so we can move on. Thank you. I appreciate that too.
I actually got it, Mr. Ko.
Okay, so this next one is a very common type of question that you see. The graph of a velocity particle is moving on the x-axis is shown to the right. The particle starts at x equals to 3, then at when t is equal to 0. So they're telling us automatically that this particle is starting off at 3. You don't see that in the graph. Please, why don't we see that in the graph? They told us we start at 3. So if this was my particle moving from left to right, we're actually starting on 3. Okay? But why don't they show it here? Because this is velocity. Velocity has nothing to do with position. When your mom says, how fast were you driving on the freeway? Right? Like 20 miles an hour, right? Or 30 miles an hour, 40 miles an hour, 50 miles an hour. But it doesn't tell you where you're driving at what specific position. And that's the problem. It doesn't tell us what specific position we're at. Find the part where the particle is at the end of the trip, and then find the total distance traveled. So they're asking us two things. First, find the particle at the end of the trip. So that's the location. So how much did we travel here? How much did we go back? And then how much did we go forward? Right? We're looking at where is the position of this particle. Now these are just three triangles. Half base times height. 2 times, that's a 2. 2 times 2 is 4. Half of 4 is 2. That's 2 right here. Oh man, stupid trapezoid. Okay, the trapezoid is 1, 2, 3, 4, 5. 1, 2, 3. Whoops. Half base times height. It's 5 plus 3. The height is 2, 1/2. That becomes 8. Negative 8. Sorry, this is hard to see. Negative 8. All right. The bottom's negative 8. And the triangle here is half base times height. I'm seeing the base is 1, 2, 3. 1/2. Height is back to 2. And that's going to be 3. So if my particles start off at 2, we went forward to 5. We went back negative 8. So we're at negative 3. And then we move forward again by 3. And then now we're at 0. Okay, we plus 2. We minus 8. And then we plus 3 again. So we're at 0.
What does it mean when it says it starts at 3?
So it means, let me give you a different way of looking at it. Let's say we are in a building. Okay, we're in the building. And I'm starting on the 3rd floor. I'm not starting on the ground floor. I'm on the 3rd floor. And then you added 2 floors here. So we went from the 3rd floor up to the 5th floor. From the 5th floor, I went down 8 floors. So we're in the basement now. 5 minus 3 is, so 5 minus 8 is negative 3. We're on the negative 3 floor. And then I went back up 3 floors. We're at 0 now. So the initial value is where we're starting off on this number line. So we're not starting off at 0, we're starting off at 3.
But so we still include all of the spaces though on the graph.
Yeah. So another way of looking at this is your final position is your S, in this case, they use X, right? Your X at 10, that's my final position, is my initial position plus the displacement. How much did we move since we started? Well, when we started, we went 2 minus 8 plus 3. Are you guys okay? That's my displacement. 2 minus 8 plus 3. That's how far we moved from my initial position. My initial position was 3, though. So this adds up over here to 5, negative 3. So 3 minus 3 is equal to 0. And the thing about these graphs, they can be confusing, but once you've tried them a little bit and you understand that these are just area graphs of velocity, and you take the area of velocity, it gives you position. Did we move forward or did we move backwards? So where's the particle at the end of the trip? That's our displacement plus our initial position. And the total distance of the particle, how far did we travel in the end? Well, we went forward by 2. We went back by 8, but that's me counting forward again because that's me working here. And we add everything. That's its absolute value. That's going to be 13. Okay. I think these are fun once you kind of get the hang of it. So where's the particle at the end of the trip? I'm going to write it's 0. Yeah, fantastic. And how far did we travel? We traveled a total of 13 meters. Fantastic. Yay. And then the next question is very similar. I give you guys actually a bunch of these that are kind of similar to each other. Just so you guys can work it out. Different shapes, different triangles. All right. Now, using these skills of velocity and acceleration, these are what we call rate problems also. These are essentially what we call rate problems. These are rates. And is it miles per hour a rate? Meters per miles per hour, meters per second. These are rates. But so is this problem that we're going to look at right now. And this one is a little tough because it's a situation. And people join the line for a particular amusement park at a rate r. And this rate r is almost like velocity. Here's our velocity problem on the right. Adding and subtracting. Given the graph shown to the right, there are 500 people waiting in line at noon. So at noon, the start of this graph, they're already, let's call this S of 0 is equal to 500, right? There are already 500 people here. If the ride can take 700 people per hour, how many people are waiting at 5 p.m.? Okay, so the rate of the ride is 700 people per hour. And rides can go up to like almost 2,000 people sometimes if it's a really crazy capacity ride. Okay, 700 people per hour. Now, this is what we're trying to say. I have people lining up, and this is the rate of people lining up per hour. Okay, this is the rate of what people are lining up per hour. Now, this part is confusing, and if I draw this a little differently, what if I said instead of it being curved, what if I draw you a different graph just to get the idea here? The rate is 800 people for 1 hour. How many people lined up in 1 hour? This is the rate. 800 people, right? People per hour times 1 hour. Isn't that 800 people lined up? Okay, here's the idea. If I give you a rate and I multiply by a time, that's our value. Okay, 800 people per hour times hour, the hours cancel out. We have 800 people line up. In this case here, is that a constant value? Is it a nice straight line across the way? It's not, it's changing, but it doesn't change the way I found it. It's still just the area. So I want you guys to take a look here. What is the area of each of these trapezoids? Okay, that's one way of doing it. Okay. If not, you can change them to triangles however you want, but I'm going to show you guys this way of me looking at it. Just a bunch of trapezoids. This is 600 and 1200. Please add them and divide it by 2. Now, why am I going to divide by 2? Remember the formula is 1/2 height b1 plus b2. And I'm going to show you this is actually a really fast pattern. In your head, what's 600 plus 1200? 6 plus 12 is 18. What's the height? Right, that's a 1 here, right? So ignore it. What's half of 18? 900. There are 900 people that lined up in this period of time between noon and 1 o'clock. How many people lined up between 1 o'clock and 2 o'clock? You could do the same math, but isn't the left side here looking just like the right side? Save time. We also add up 900 people here. How many people add up from 2 to 3 o'clock? The same trapezoid, isn't it? Thank you very much. And the last one is a little bit bigger, but it's okay. It's 1200 and 900. Please add those up. 1200 plus 900 is 2100.
Mr. Cole?
Did I make a mistake? What's up?
No, I was saying the time.
Oh, running out of time. Oh my gosh, hate my life. Okay, real quick. Those divide out 2100, right? So how many people queued up? This whole thing, how many people queued up? Add. That's 2700 plus 2100. That's 4800. Okay, 4800 people lined up. But how many people can ride the ride? 700 people per hour. From noon to 5 o'clock. That's 700. That's 700 times 5. There's 3,500 people that were able to line up. Now here's the problem. We had 500 people to start. 500 plus 4,800 that queued up, minus the 3,500 that were actually able to ride the ride. And that's the number of people left in line. Okay? So this is kind of cool. We're able to do this. This is a very easy way of looking at it, but if you actually look at Six Flags, they have numbers like this. We have people, the rates of people that queue up, the number of people that can ride the ride, so the capacity of the ride. So it's kind of cool. Anyways, so these types of questions are very similar to motion lines, motion equation, but we just switched the word from velocity to people. All right, that's it. Good luck with this. Thank you very much. Sorry, guys.
All right, bye.